Swayam Prabha. Digital India. Educated India.
So far we have discussed kinematic analysis and synthesis of planar linkages in general. From today's lecture, we will start discussing only on some special classes of mechanisms. To start with, let me talk of what is known as straight line mechanism. What do we mean by straight line mechanism? By that we mean that we have to come up with a planar linkage consisting only of R pairs such that a particular point on a floating link as the mechanism moves will generate a straight line. So, only R pairs. A point on a floating link. Floating link means the link which is not connected to the ground or the fixed link, that is not connected to the frame, like the coupler of a 4R linkage. The crank and follower are not floating links, it is the coupler which is the floating link. A point on a floating link should move along a straight line. One may wonder why take all the trouble to generate a straight line by using only R pair, because we know if we have prismatic pair we can always generate straight lines. So, let me say why not prismatic pair? There are 2 points to remember why not a prismatic pair. First is prismatic pair implies more friction and wear, difficulty of manufacturing a prismatic pair as compared to an R pair, that is difficult construction and maintenance. Moreover, we should also remember that in a prismatic pair we do not generate a straight line, we rather copy an existing straight line. So, prismatic pair only means copying an existing straight line. I must emphasize this difference between copying an existing geometric figure and generating a geometric figure. For example, when I draw a circle using either a revolute pair or a compass, we do not copy a straight line, rather a point is constant to move along a circle. It is not that I am taking a circular object then drawing along its periphery. Whereas in a prismatic pair there is always an existing straight line and I am just copying it. And the third thing to remember that in the early stages of mechanization, it was very difficult to make a long prismatic pair. That is why the straight line mechanism historically is very important. In fact, this is one of the first mechanisms which challenged both the ingenuities of both the engineers and the mathematicians to how to produce a straight line without copying an existing straight line. That means how to generate a straight line using only R pair. The first person to come up with an approximate solution is James Watt. In Watt's engine, as you know, the cylinder and the piston must form a prismatic pair. But during James Watt's time, it was not possible to make a piston and a cylinder with closed tolerance. There was a lot of clearance between the piston and the cylinder. So he wanted to guide his piston along a straight line by using one such straight line mechanism. And Watt's mechanism was the first approximate straight line generator or approximate straight line mechanism. Well, now it is known that it is not possible to generate an exact straight line by a 4R linkage. No point of a coupler with any dimensions of all the links can produce a perfect straight line. However, it is possible that a portion of the coupler curve can fairly reproduce an approximate straight line if the dimensions or the link lengths are properly chosen. That is precisely what James Watt did. He talked of a non-Grashof double rocker of suitable link lengths such that the midpoint of the coupler generated an approximate straight line. Now I shall show you the figure and explain how it is achieved. This figure shows the sketch of what is known as Watt's approximate straight line mechanism, as it was first designed by James Watt. As we notice that this is a 4R linkage with fixed link number 1, link number 2 is O2A, the coupler link number 3 is AB, and O4B is link number 4. In this linkage, the length of O2A is same as that of O4B. O2A is equal to O4B. C is the midpoint of the coupler AB, that is AC is equal to BC. And the total link, other link lengths O2, O4 to O2A to AB are in the ratio of 10.77, 5:4. These ratios were obviously arrived at by trial and error such that when this linkage moves, this midpoint C generates a figure of 8, and in this figure of 8 there is a portion from C1 to C2 which is a very good approximation to a straight line. In fact, the difference between this straight line and this curve is hardly noticeable. What James Watt did is he connected his piston rod to this point C, and as this linkage moves, the piston goes almost along a straight line. As we notice from these ratios that L max is 10.77 in some unit and L min is 4. So L max plus L min is 14.77, which is much greater than L prime plus L2 prime, that is O2A plus O4B, which is 2 into 5, 10. So this is a non-Grashof linkage, which means it is a double rocker. Let us now look at the sketch of another approximate straight line mechanism which is known as Evans or Grashofer mechanism. In this mechanism, the fixed link is O2, O4, O2A is one of the cranks and O4B is the other link connected to the frame, and AB is the coupler. Here the coupler point C is taken on the extension of AB, and as this mechanism moves, the point C again generates this figure of 8, in which the portion from C1 to C2 is again a very good approximation to a straight line. As we see in this mechanism, O4B is equal to AB is equal to BC. AB is same as O4B, the link length is also equal to BC. And the other link lengths are in the following ratios. O2A is to AB is to O2O4 is 2 is to 2.5 is to 5.39. If we take these link lengths, then this point C on the extension of the coupler AB will generate an approximate straight line. This is known as Evans approximate straight line mechanism. Let us see what is the maximum link length, that is the O2O4 is 5.39 and the minimum link length is 2. So L min plus L max is 7.39 and AB, which is same as O4B. So L prime plus L2 prime is 2 into 2.5, which is 5. That means L min plus L max is greater than L prime plus L double prime. So this is also a non-Grashof linkage, and consequently this mechanism, just like the Watts mechanism, is also a double rocker. Let me now discuss a methodology such that I can determine a suitable coupler point in a 4R link to, for example, generate a vertical straight line. What we do, we start with a 4R linkage, say O2, A1, B1, O4. I want that as this linkage moves from this O2 A1 to say O2 A2, when the fourth link moves from O4 B1 to O4 B2, I want to determine a point on the extension of this coupler AB such that that point C generates an approximate vertical straight line. The methodology is as follows. What we do, we find what is the instantaneous center of the coupler, that is link 3 in the first configuration. As we have seen, we can extend O2 A1 and O4 B1. Wherever they intersect, that gives me the instantaneous center of the coupler at this configuration, which is I1. Now I draw a horizontal line through I1 and let AB extended meets this horizontal line at C1. Then I know that at this instant I1 is the instantaneous center for the coupler 3. So the velocity of the point C will be perpendicular to I1C. C1. That means C1 moves along this line. Now in the second configuration, I again locate the extension of O2A2 and the intersection of O4B2, which gives me the instantaneous center of the coupler I2 at the second configuration. Now I draw a horizontal line through I2 and extend the coupler AB such that these two lines, this horizontal line through A2 and the extension of the coupler, meet at the point C2. So at this second configuration, the velocity of the point C2 is perpendicular to I2 C2. That means the path of C2 is a vertical straight line. Now obviously this distance A1 C1 will be different from this distance A2 C2. So what we do, we take a point C on the extension of the coupler, say here C, which is the mean of these two distances, that is half of A1 C1 plus A2 C2. With this point C2, what we will see, that the path of C will be a good straight line. The path of C, this is point C2, and A2 C is more than A2 C2, and A1 C1 is more than A1 C, and A2 C2 is less than A2 C, and A1 C1 is more than A1 C. The point is this, The point C1 has a fairly good straight line here at the first configuration. The point C2 has a fairly good straight line at the second configuration. And I take a point C in between C1 and C2 such that during this entire range it goes almost along a straight line, approximately vertical. So this way we can design an approximate straight line mechanism. It must be emphasized that with a 4R link with any point on the coupler or any choice of link length, I can never generate a perfect straight line. For that we will discuss later that we have to go for linkages with more number of links, that is more than 4. Before that, let me discuss two other approximate straight line mechanisms which are historically famous, which are designed by mathematicians to generate an approximate straight line. Let us now look at the sketch of another approximate straight line mechanism which is known as Roberts mechanism. As we see, in this Robert mechanism is nothing but a 4R linkage. This is a fixed link 1, link number 2, this is the coupler, link number 3, and this is link 4. In this coupler, we choose a point C such that when this mechanism moves, the C generates this curve with a cusp here and two loops on here and here. But during this movement of the coupler C, it is C1, C2 from O2 to O4, it is fairly coincident with the line O2, O4. The discrepancy cannot be seen by naked eye, but definitely C is not going along a straight line O2, O4, but the discrepancy between the path of C and the line O2, O4 is negligible. So this is again a straight line mechanism where the straight line is generated at O2, O4. For this mechanism, the dimensions are as follows. O2, O4 is twice of AB, and O2A, AC, BC, O4B are of equal length. This link length is equal to this link length, which is also same as AC and BC, and O2, O4 is twice of this link length AB. In this Robert mechanism, the thing to note that it generates a very good approximate straight line, and the straight line is coincident with the line of frame O2, O4. Now let us have a look at the sketch of another approximate straight line 4R linkage which is known as Chebyshev's linkage. This is again a non-Grashof double rocker, and as we see in this linkage O2A, B, O4, the midpoint of the coupler C generates a fairly good straight line from C1 to C2 as this linkage moves, and this line C1 to C2 is parallel to O2, O4. Again I emphasize that the path of C is not an exact straight line, but the discrepancy between the path of C and this straight line C1, C2 parallel to O4 is negligible. The entire coupler curve looks like this D-shaped curve with a fairly horizontal portion which is parallel to O2, O4. In this Chebyshev's linkage, the link lengths are as follows. C is the midpoint of the coupler, that is AC is same as BC, and the link length AB is to O2, O4 is to O2A, which is same as O4B. That means link 4 and link 2 are again of same length, and the ratios are as follows. AB, the coupler length, is to O2, O4, that is the fixed link length, is to O2A or O4B, which are same, is in the ratio of 1 is to 2 is to 2.5 is to 2.5. So here let us see L max is 2.5 and L min is 1, that is L min plus L max is 3.5. Let us now look at the link lengths of this particular linkage. What we see, AB, the coupler length, to the fixed link length O2, O4 to the input link say O2A, which is same as O4B, are in the following ratios. 1 is to 2 is to 2.5 is to 2.5. So, the minimum length is AB, the coupler link, which is of unit length, and the longest link is say O2A, which is of 2.5. So, L min plus L max is 3.5, which is less than L prime say O2O4 and L double prime, which is 2 plus 2.5 4.5. So, this is obviously a Grasshoff's linkage with the shortest link as the coupler, which means it will be again a double rocker, but this is a Grashoff double rocker. This is a Grashoff double rocker, but the point C generates a fairly good approximation to a straight line. Next, we shall show how did we get these link lengths. The idea is that this point C1 is exactly above O2 and this point C2 is exactly above O4. What we do, we determine the link length of this symmetric linkage, that is O2A equal to O4B, such that the velocity of the coupler point C at C1 is horizontal direction. Same is true for C2. When the coupler point comes to C2, again the velocity of this coupler point will be horizontal, and at the midpoint of C1 C2, that is at the midpoint of O2 O4 here, in that configuration again the velocity of this coupler point will be horizontal. If I say that at these three locations the velocity is horizontal, that is the coupler curve is horizontal, then there is very little deviation between these 3 points. Very little deviation of the coupler curve from this straight line C1 C2. It is exactly tangential to the coupler curve at C1, at this midpoint, and at C2. It will be clear when I explain this with the help of sketches and get to these relations. This can be derived by the simple consideration that at C1, C2 and at the midpoint, when C occupies the midpoint of C1, C2, the velocity of the coupler point should be horizontal. That means this horizontal straight line will be tangential to the coupler curve at these 3 locations, and in between there is hardly any difference between the coupler curve and the horizontal straight line. So, let me now calculate the required ratios of these L1, L2, L3 and L4 such that these 3 configurations are possible. We know because of this symmetric linkage L2 is equal to L4. If I consider this configuration, then I get L2 squared is L1 squared plus L2 minus L3 whole squared. So, I write L2 squared is L1 squared plus this is L2 because L4 is L2 minus L3. So, L2 minus L3 whole squared. If I expand, what I get from here is L1 squared plus L3 squared is equal to 2 L2 L3. Say this is equation 1. From this configuration what I get, L2 squared is this vertical height which is same as this vertical height. So, I can write L2 squared is this vertical height is L2 minus L3 by 2. So, L2 minus L3 by 2 whole squared plus this horizontal squared. This horizontal is L1 by 2 plus L3 by 2. So, plus L1 by 2 plus L3 by 2 whole square. Now, if I expand this, what we get, L2 squared cancels.
So I get L3 squared by 4 here, L3 squared by 4 here. So that is 0 equal to L3 squared by 2 minus L1 squared by 4 plus L1 squared by 4 plus L1 L3 by 2 minus L2 L3. So we get L3 squared is, goes to this side, 2 L2 L3 minus L1 L3 minus L1 squared by 2. Now here I have seen 2 L2 L3 is L1 squared plus L3 squared. So if I write that here, I get L1 squared plus L3 squared minus L1 L3 minus L1 squared by 2. So L3 squared cancels, L1 squared by 2 is L1 L3, that is 2 L1 L3, which means L1 is 2 L3. So from this expression, if I cancel L3 squared from both sides, I am left with L1 squared minus L1 squared by 2 minus L1 L3. That is, L1 squared is twice L1 L3. If I cancel one L1, what we get? L1 is 2L3. That is, the fixed link length O2O4 is twice of the coupler length AB. Now, using this expression in equation 1, what we find, it is L1 squared is 4L3 squared plus L3 squared is 5L3 squared is twice L2 L3, which means L2 is 5 by 2 L3. So overall what we are getting, the coupler, the shortest link length AB, if I call L3, then O2O4, the fixed link length, is turning out to be 2L3, and O2A and O4B, which is L2, which is equal to L4, is 2.5 times L3. So these are the three ratios that I showed you earlier. So this is the Chebyshev's approximate straight line mechanism, which generates a very good straight line path in this range C1 to C2, then it goes high above and makes a D-shaped curve. So far we have discussed 4 different 4R linkages which are all capable of generating approximate straight line mechanism. They were in order. One was called Watt's linkage or Watt's mechanism. Then we discussed Evans mechanism. Third one we discussed was Roberts mechanism, and the last one was Chebyshev's mechanism. Out of these 3 were non-Grashof, double rocker, and this one was a Grashof double rocker. If we remember, these two with those particular dimensions mentioned earlier were capable of generating figures of 8, in which a fairly long portion
was in approximate straight line. In this Roberts mechanism, we had a cusp, a curve of this type, where there is a cusp and this fairly approximate straight line portion which was coincident with the locations of the fixed links, fixed hinge O2 and O4. Whereas in the Chebyshev's mechanism, we had a D-shaped curve which had a fairly approximate straight line portion which is parallel to the pivot line O2, O4, fixed line O2, O4. Now we shall demonstrate these four mechanisms through models. You should watch how good an approximate straight line all these coupler curves are. These are all 4R linkages. We considered a particular point on the coupler, and the corresponding coupler curve has a fairly good portion of approximate straight line. We will now demonstrate these four mechanisms through models. This is the model of that Watt's approximate straight line mechanism. This is the point O2, this is the point O4, this is A, this is B, that is, this is the coupler, and let us concentrate on this midpoint of the coupler, that is the coupler curve generated by this midpoint of the coupler. As this mechanism moves, we notice that this midpoint is generating this figure of 8, and in this figure of 8, from here to there, it is a fairly good approximation of a straight line. This is the figure of 8 that is being generated, and from here to there, this portion is a very good approximation of a straight line. This is the Watt's approximate straight line mechanism, which, as I said earlier, James Watt used this particular point to guide the piston within the cylinder. This is the model of that Evans or Grasshopper 4-link mechanism which can generate an approximate straight line. This is the point O2, A, B, O4, and this coupler point C is taken on the extension of the line AB. With the proportion of the link lengths, as I said earlier, as we see, as this mechanism moves, this coupler point generates this figure of 8, in which from here to there, this portion is a very good approximation of a straight line. From here to there. As we notice that both the Watt's mechanism seen earlier and this Evans mechanism are double rocker. Neither link 2 nor link 4 can rotate completely, and as we see that this rocker is crossing the line of frame, which implies that it must be a non-Grasshopper double rocker. This is the line of frame, and link number 4 is coming below this. So this is a non-Grasshopper double rocker, just as in the case of a Watt's linkage. This is the model of that Roberts approximate straight line mechanism. This is O2, A, B, O4, and this is the coupler with this coupler point as the C. Now, as this mechanism moves, we should notice that this coupler point C on link 3 is generating almost the straight line O2, O4 with a very close approximation. And here there is a cusp, and there are two loops at O2 and O4. This is again a non-Grasshopper type double rocker, because both the rockers are crossing the line of frame, but they cannot rotate completely. Both of these are rockers, but they are rocking above and below the line of frame. So this is a non-Grasshopper double rocker with a very good approximate straight line generation between O2 and O4, this coupler point C. This is the model of the Chebyshev's
4 link mechanism which can generate an approximate straight line by this midpoint of the coupler O2, A, B, O4, and this is the point C which is the midpoint of the coupler AB. As we calculated the link length ratios, this O2, O4 is twice of AB, the twice of coupler link, and this link length and this link length are equal and is equal to 2.5 times this coupler link length, coupler length AB. If this is unity, then this is 2 and these two lengths are 2.5. If we move this, we should notice the curve generated by this coupler point. As we see that this portion of the coupler point is a very good straight line, very good approximation of the straight line, that is, this is above, this is one configuration that we considered where O2, A and AB are vertical. This is C1. This is again O4B and AB are vertical, and this is C2, the coupler point, and this is the symmetric configuration which we call C, O2, A, B, O4 with this point as C. So, this is the Chebyshev, which is again a double rocker, but as we see the rocking is all above the line of frame. So, it is a Grashofian double rocker, unlike the previous three.